Um, yeah, so we'll talk about sequential decision making and mostly open up some formulation and notations to think about problems like reinforcement learning or imitation learning. Okay, so the goal of today really is trying to lay a foundation for the next few lectures, really the next 2 months. Yeah, so maybe you've seen Markov decision processes before. Who has seen MDP before? Okay, wow. So maybe this is like mostly for the refreshing sake. If this is the first time you see this thing, when I first learned this stuff, I felt like there are tons of notations, like a lot to go through. At first, it feels kind of hard to grok. But once you get used to it, like a lot of these ideas make sense, right? So we'll focus on one version of MDP, the finite horizon one, mostly because it relates or it gives somewhat more clarity or clean presentation for the next few lectures. But one of the ideas about MDP is really the idea of Bellman or dynamic programming, right? So we'll talk a little bit about how do you formulate these ideas using the concept value functions. And how do you solve an MDP, right? So we'll mostly look at this problem from the standpoint of planning, right? So planning really means like you actually look at this environment or look at this MDP from God's view, and you just want to solve a planning problem. It's like there's nothing really to learn. Like the system is completely transparent and visible to you, but how do you still solve the optimization problem? Obviously, the more realistic and more practical problem is learning, where maybe the MDP is not entirely presented to you. You have to like poke different parts to learn things like transition function and reward function. We'll get to that. But today we'll really try to lay the foundation, getting used to a set of notations and basic ideas. Okay, cool. So yeah, I promise there'll be some notations, but it's not crazy. So Markov decision processes. This is a general formulation. It involves a few elements. So there's a state space S, basically where you are in the map. You're solving a decision-making problem, so there's action. You have reward function. This is for the sake of this course, reward function is an interesting concept. In general, you can think about it as a random variable. Basically, at some state, you take some action, it gives you some random reward. So I'm going to use this notation. So I'm going to assume the reward is bounded. And without loss of generality, I assume everything is between 0 and 1. You can rescale it or shift it if you want. The key is that, in general, you might think about it as a random variable. Okay, so what you get for taking an action at some state is a random reward drawn from this distribution specified by the reward function. You should treat it as a probability distribution or a random variable. Okay. So this is random. The point of sequential decision making is that you're not making one decision, not a one-shot decision, right? So you make one decision, you interact with the environment, you impact the environment in some way, maybe by positioning yourself in a different place, maybe you change your temperature a little bit. There's some modeling you have to do around this interaction with the environment, usually captured by what's known as the transition operator. So If you take an action at some state, it will move you to a different state. Again, we allow these things to be random. So it could be a randomized or probabilistic transition function. There's some randomness involved. But for a lot of the problems you might care about, the transition might just be deterministic. Like you make an action, you know for sure you are going to end up in the next state. There's only one place you will end up with. Like some modeling of a large language model using MDP is like deterministic, right? So like the state is sometimes a prefix of a sentence you have written down so far, and the action is usually a next token, right? So if you generate a next token, you just lengthen this language generation by a little bit, and that defines the state. So oftentimes that's regarded as deterministic. Okay, and to start with, you usually have some initial state. This is like a distribution. Again, it could be random. So the initial state, which I would denote as S0 or S naught, is just drawn from this distribution. Okay. So far, this doesn't say anything about being Markov, right? So this could, in principle, model any form of sequential decision making that can be arbitrarily complex. So the key property we should think about is Markov or Markovian. Markovian. So what's the Markovian property? That doesn't, for those who are expert in MDP, how would you describe it?
Memoryless.
Memoryless. Okay, that's what does that mean?
It means the only thing you really care about is the state you're in, not the path you take to get there.
Excellent. Yeah. So Markovian, you mean memoryless or like you're forgetting, right? So when I have a meeting with my grad students, I often say I'm Markovian because I don't sleep well anymore, and I don't remember anything from last week. So mathematically, sometimes it can be written as like, the state and reward from current steps is like independent of 2 steps ago, condition on what happened in just the past step. Okay. So I realize I haven't defined what H means. Let me introduce those notations. So I'm going to focus on a version of MDP that is finite horizon. There are other versions like infinite horizon that it never stops, and usually you attach some sort of discounted factor there. We'll focus on the finite horizon one because it's cleaner for some of the later lectures. So horizon is just like how far, what's the total length you're going to engage with some environment or with the MDP. So in general, you're going to think about some sort of trajectory of length capital H. At some point, I'm going to use tau to denote trajectory, which really just means I'm going to start with some initial state, take an action, get some reward, do it again up until H minus 1 steps later. Okay. So Markovian process, the Markovian property really just means like this could go on for a long time, but at some point you might think, oh, should I have perfect recall? Should I just like, look up the memory and look up the history? The environment basically tell you like don't bother. It could be useful maybe to design your decision-making process, maybe not. But for the environment's sake, in terms of how the state might evolve, these previous history or interactions don't matter. Okay. So yes.
Basically, the transition operator is independent of the previous states.
That's right. And it's explicitly written in this form because like it's only a function of current state and action. Yeah. So there's also a discounted version. And infinite horizon. We won't cover it today, mostly because I can only think about one thing at a time. The notations get swapped around. We did post some lecture notes by Nan Jiang from URUC that has a decent treatment of the sort of the same material we'll cover today, but in the language of infinite horizon and with a discount factor. Okay, so we won't talk too much about that. Okay, so we are interested in decision making. Therefore, we should think about how to make decision making with some policy. Okay, so we're going to talk about policy. What is a policy?
From the states to the probability distributions of actions.
Yeah, so your answer is mapping from state to probability distribution of actions. That's a valid definition. That would be the kind of policy we care about. I'm going to start with something that sounds extremely general that might hurt your brain. Like, in general, pi could be, I'm going to write this h a little differently. This is the cal h. For you, it's like math cal h look different. Okay. So what does this mean? Like, in full generality, it should feel weird, in a second. Like, but in full generality, like the kind of decision-making process could really take any partial history. Okay, but your gut feeling is you should not need to think about it because of the Markov property. Okay, but in general, nothing stopped you from thinking about this crazy class of policy that look at the entire history and make a decision. Okay. Right, so we'll briefly talk about this. It would be nice to never look at this because this seems hard to handle. The kind of policy we'll mostly think about is called non-stationary. Markov policy. So basically what you describe, like if I look at a state, I should just use the current state as the only information I care about. Actually, let me more than current state, and since it's finite horizon, you actually care a little bit about the current timestamps. All right. Quick correction. Okay. So what's the idea here? So this seems crazy large. All partial history they feel clunky, right? So the idea here is compress everything down to current state and time step. Okay, so and sometimes I might write this as, we might denote this as pi of h, okay, meaning like the MDPs has already taken place for small h number of steps. What should I do now? And intuitively, you should care a little bit about the current step you're in. Like, if you're already at the end of the game, at the end of the MDP, the decision you make might look a little different had you been the first step of the MDP, right? So the time horizon left from now on should also matter in the decision. So this is sort of what non-stationary means. In like, if you have stationary, sometimes you read papers, you see some stationary. Stationary means not depend on h. Okay, so the decision you're going to make or the policy you're going to use doesn't depend on which time step you're in. So this sort of formulation is more common when you're in infinite horizon discounted setting, because what's the point of time step anyway? Because this process will go on forever. For us, because we have finite horizon, some of the derivation we have will carry this time step around. Okay. So the objective we care about, maybe it's obvious to you, is the total reward. So if I have a policy, maybe it's Markov, maybe it's not. I care about the sum of the reward. And I'm going to write it as and importantly, I want to explicitly acknowledge that the set of decisions is generated by the policy pi. Okay. Right, so for Markov policy, you generate these decisions without looking at the full partial history. But in general, you might actually be non-Markov. So how do we optimize this? This is a very general formulation. Suppose you live before Bellman, like, what will be the first thing you think of for solving this? What would be a brute force way to solve this? Okay. So suppose I tell you just search around, find the best policy in the Markov policy, and even better, let's only think about the deterministic policy, meaning like this is not exactly random, like this is like probability, putting all of the probability onto one action. Like, so this is called deterministic policy. If you start thinking about a naive solution, like if you just think, well, I'm going to do what people are very good at these days, scale it up. I have so much money. I'm going to just do the brute force way. Okay. So one way you can think about doing, it's not a good idea, but it helps appreciate the complexity of the problem, right? So like, at most, that can be at most, how many deterministic policies can there be? Well, so for every state, and every time step I have to choose some action. How many is that? So the number of so this is like number of actions, let's assume is finite. And number of states, an exponent in times h. So this is like the number of deterministic policy. Okay. So if you believe that you have tons of money, you think you can buy enough computer or memory to solve this? Probably not. Like for reasonable h, you hit the exponential blow. So in principle, you could do the brute force, but maybe you will exhaust all the atoms in the universe to even record this many policies. So why is sequential decision making hard? Part of the difficulty is like you're making not just one decision at current step. You sort of have to watch out for your impact or the downscaling effect for the current action to the future state or the future reward you might get. So together you're kind of making like h different decisions, and it also depends on what state you're in, right? So the horizon can be a little bit intimidating. Luckily, we have some interesting property, right? So like we're in a Markov decision process. So the environment is somewhat forgiving in the sense that this is Markovian. So it's, the history before time step don't matter, and it will be helpful for thinking about how to solve the problem. Like so when you heard the word Markovian, you're just thinking about it's forgiving in some way. There's a stupid way to remember this, like if you choose a PhD advisor, choose a Markovian one, because whatever this person tell you to do from last week, they won't remember the week later. So a little bit of life advice. Okay, so how do you do better than brute force search, right? So the word Bellman is somewhat analogous to the idea of dynamic programming. So if you've taken an undergrad algorithms course, you might have heard of the idea of dynamic programs. And these two words, Bellman and dynamic program, is kind of like interchangeable in some ways. So lean on the ideas of what is called the value functions. Okay. So I will define it for Markov policy. It will also make sense for non-Markov policy that depend on history, but we won't get to it for good reason that we'll show later. So suppose you have a Markov policy. There's two sort of value function. State value function, usually denoted by V. And for finite horizon setting, I will also carry this time step little h around. So it's a state value function, so it takes state as input. Okay, and it just merely means like if I use policy pi from now on to make the decision, what is the objective value I get? Nothing too interesting other than writing out this definition. But we'll play with this object in different ways that will derive how to solve MTP. So the way you read this, like when you see a thing like this, is the value of pi. The value of pi when you're in state S, or and or when you're at state S at times that H. So that what's the value of using pi? It generates some revenue, it generates some rewards, and it's captured by this function. Okay, so and there's also what's known as the action value. Sometimes called state action value, but action value is also the common name is shorter. Okay, so what does that supposed to mean? Like, so it's almost the same as the state value function, except I single out, I put an additional notation for action here. It's basically the same quantity, except that I deviate a little bit, right? So, take. This is the quantity I get. This is the total reward I get for taking action A now, and then follow policy pi. Okay. This is pretty much the same thing, except that you want to follow the policy pi from now on. Okay. So the difference of these two things will play a role in the remainder of this course and this lecture. So, yes.
Is it a h plus 1 to hi, big H minus 1?
That's right. So this is like the next step, and to the end, I will follow pi. But from now on, I'm fixated on this action A because I believe there's something magical about action A. And I want to compare, a lot of the derivation from now on is about comparing these two things. Just follow pi from now on, or just switch the current step. Yeah.
The reason you also condition on the future that you try to predict all of the future rewards of a single action at time h.
Yeah. So maybe a different way to answer your question, like the idea of Bellman or the idea of dynamic programming. Okay, what's the philosophy behind this? So like life is hard. Like we're making sequential decisions over a long time horizon. The usual advice you get is focus on right now. And the way you get to focus on right now is basically decompose like the decision of the current step and whatever you might get later. So the idea we'll show in the next slide is how to decouple the current decision making from future. And then the focus of the principle of dynamic programming is like, look at this decoupling and divide and conquer. So 99% of the ideas in computer science is divide and conquer. You have a hard problem, you break it down and beat it to death. Sorry, this is a little violent, but you see what I'm saying. Okay. Okay, so Bellman equation. So the Bellman equation will use the Markovian property. So the point of Bellman equation is the decoupling I'm talking about. Right? So making h decision simultaneously is hard. decoupling is allow you to think for the current step first, assuming what you might get later on by following some plan, like some policy. So the Bellman equation is basically doing this form of decoupling or decomposition for these value functions. Okay, so I guess I missed an S here. This is the same quantity as above. There is like the most obvious definition, like you sum the rewards. If I put you at state S and you have some number of steps to go, what's the total reward you will get by following policy pi. Here, this is doing some sort of decomposition. Like, what's the value of this policy? Well, today I'm going to get some reward. And then I will land in some random state according to the transition function. I'm hiding something in an expectation here. Like the SH+1 could be random. But let the plan pi worry about tomorrow because this is the value it will get by following this plan, by following this policy pi. Okay. And you have this similar thing here. Okay, it's the same sort of decomposition, except that I'm committing to take one action, a particular action that may not be suggested by pi. So I want to make sure that I'm doing well today. Like I'm going to choose some action A. It will immediately generate some reward. And let's not worry about tomorrow because we already somehow has some plan, some default plan pi that allow us to go from now to the future, right? So this is sort of like allow you to decompose the decision you make today and its downstream effects in the future, okay? And breaking down problems to small pieces is easier to bite, okay? And if, in case it's not obvious to you, like, if you roll back to the first time step, this objective is really just the state value function of the initial state. Okay. Okay, so some notations, some getting used to, but once you get used to it, the idea is obvious. Okay, so yeah,
The action value function,
yes.
condition on the, that h+1 action will be dependent on
Oh yes.
policy, but is it also conditioned on the transition function? Because you also, for the Q function, the next step, you also need the state.
Yeah, so I'm hiding some randomness of the environment here, like the future state will be drawn according to the transition that's hidden in the expectation. Yeah. Good question. Okay, so once you write down this quantity, like, it's not that hard to derive the optimal policy. So how do we get optimality? Okay, so I'm going to slightly twist these two equations by introduce some elements of being greedy. Okay, so I'm going to define a set of functions. I'm going to try to call it V star. Start from step 1. And they're defined in the following form. So you should think about this as the optimal value. This is actually called the optimal value. It's hard to think about, like, this is exactly the thing we optimize. We don't know how good it is. But then if you put yourself at the end of time, right, like, at the end of time, there's nothing else to do. You're on your deathbed. Okay, I don't want to be morbid again, but you're graduating and, like, there's no more homework to do. You just do nothing and get 0. Okay. Yeah. So the base case is easy. Like, at the end, there's nothing else to do. You have no more cumulative reward to gain. At the end, it's easy. But then you can do some sort of backward induction. This idea is called backward induction, which means, like, for all the states, so this is like for any state, this is 0. And in the previous steps, like, now you can do some sort of backward induction, right? So, like, you roll back a little bit to time step h minus 1. You still have one step to play. What do you do? Well, it's obvious, like, you should just, tomorrow there's nothing else. Let's just be maximally myopic and greedy. You pick the one that maximize today's reward. But then you can start backing out to time step h minus 2. So this exercise is really captured by this recursive relationship. This is the idea of dynamic programming. Okay, so we have a base case of at the end of time, nothing matters anymore. Okay, so that's easy. At time step h minus 1, you kind of just need to think about the current time step, like h minus 1, because this is going to be 0. Okay? Like at h minus 1, you will fill in these values. Okay? At time step h minus 2, okay, what do you do? Well, you want to choose a action for today's state, anticipating there will be some downstream effect of how to optimally act. Right? So assuming I get to optimally act from whatever state you take me to, what will be, like, the best way to optimize the sum of today's reward and the downstream cumulative reward? Okay? So another way to think about this is, if someone promised you how to optimally act from now on, all you have to focus on is make the best decision today. That's making your life pretty simple. This will be the objective you have, right? Like, If someone, no matter where you go, I'm going to tell you how to act, and I also will tell you how much money you will get from following what I said, following what the oracle would tell you. Then all you need to do is like computing a bunch of sums of two terms. Right? So this is the whole idea of Bellman. Okay. So you can prove a theorem. Right? So maybe like it will sound obvious, but I'm going to state it anyway. So first of all, if you consider all possible policy, including those that might be very complex, so I erase the notation, but this is going to denote all possible policy that map partial history to actions. You can think about how much value you get, how much objective value you get. But you will not do better than V star. Okay, so this V star, that is the set of V star values that is defined recursively, determine how well you can do. Okay, so, and you think a little bit about this statement, it's a little interesting. Like, you know, this includes like crazy policy that use the history in some funky way. But being crazy is not going to help. This statement is basically like, you know, being crazy about what happened in the past will not get you a better values. And there'll be a proof, but basically, you're just using the Markovian property of the MDP. Okay. And obviously, once you have this V star value, you can define a policy that's just being greedy about this. And at every time step, you just make the greedy choice. Exactly the same thing, so it's not super interesting. I'm just putting max here to make it an argmax. So this policy achieves optimal reality. Okay, so what's the takeaway? Well, this is not a crazy computation to do. Like you just do some sort of backward induction. Start with a trivial case at the last time step. You do nothing and get 0. And gradually you roll back and solve this recursive equation. Okay? And what came out of that is that, well, first, this defined the optimal value you can achieve by solving an MDP. And you don't actually need to think about all possible policy because the Markovian policy that's greedy, acting on, like this is like implemented by a deterministic Markov policy that only depends on current state. This will achieve the optimal value. So you might find that this is maybe stating the obvious fact, like, you know, the environment is Markovian, of course, like just take a Markovian policy, you get optimal value. Yeah, sure. Like there's a proof behind this. It's not always true. Like what I say is not always true. Like, you know, there are certain type of environment where you don't get to, for example, if you don't get to directly observe the states, like this is sometimes called POM DP, like partial observable, like you might actually use a history in some interesting way. But in this setup where you get to see a state, being Markovian is sufficient. Okay. Any question? Yes.
The distribution where you set for S prime should be conditional, P as given A, or is that joint?
This is a transition operator. Take state and action as input.
Ah, I see. So you marginalize over S and it's up to 1.
Yeah. Okay, so this is a theorem. The theorem really just said being Markovian and greedy with respect to this recursive equation is optimal. There is an analogous definition that is in terms of Q. Actually, this sort of equation is called Bellman optimality equations. So in contrast to Bellman equations really just highlight the idea that you can decompose the values, like the reward as a reward you get today plus like whatever value you might get from tomorrow's on. This is like knowing the same reasoning about this decomposition, being a little greedy about it. And if you get to be optimal at the last step, you can back in and ensure this optimality propagate all the way through the first time steps. Okay. There's also a Q action value version of this. I'm going to write down, which equals you do the max here. It's kind of the same thing in the sense that this max over A prime, just make sure that whatever state you end up with, you achieve the V star. Okay. So this recursive definition not only is useful for defining the optimal value, but it's also an algorithm itself. So this equation, or it's just like these two equations, defines an algorithm planning algorithm is really just like find a pi star that optimize J pi, okay? And this recursive relations, or if you actually do a computation writing down this set of values for V star S H, this algorithm is called value iteration. Okay. I mean, there's one more step, which is like, do the argmax to actually get the policy out of it. But value iteration is just like do this backward induction to back out V star. You can for this lecture you can almost think about everything can be stored in a lookup table. You're just filling out a large table, each like something that looks like this, like for every times of h, for every state. I'm going to put in some value there. The dynamic programming, or in this case, the procedural value iteration is just trying to fill up this table. And once you have the table, you also define the optimal policy. Okay. Okay, so let me say a few more things about planning or how to solve MDP. Like this will open up some of the basic principles of the next few lectures. So we'll actually spend more time in a different kind of paradigm. So this is called value iteration. You just find V star and back out the policy. The kind of algorithm we spend more time talking about is called policy iteration. Okay, so as the name suggests, value iteration is about iteratively update or filling up the lookup table for optimal values until you're done. Once you're done, you write down the optimal policy. Policy iteration is going to iterate some policy over time. Okay, so policy iteration, you start with something. You just start with some policy. Could be random, could be arbitrarily bad, doesn't matter. And then you compute the action value function. Okay, so there's a for loop, I guess. You compute one. Okay, so this is sometimes called, the step is sometimes called policy evaluation. Okay, I have some candidate policy. I don't know how good it is. Let's evaluate the action value function for this policy. Okay. There are different ways to do it, right? Like, yeah, actually, how would you do it, right? Like, I have some policy that define how to make decision at every state, every time step. I'm going to fill in similarly like a table. So, you can follow the same reasoning of backward induction that start with the last step and gradually back out, right? So here you can start with the last step. Again, the last step is the least interesting one. Right, so there's nothing else to do at the end. You get 0. But then you actually get the same backward induction. Okay, so it's really the same equation above without a max, right? So like, actually the same thing here. Just repeated myself. But I'm going to use the Bellman equations to actually fill up this table for action value functions. So that's called policy evaluation. And then we do update, which is called greedy update. And this step is sometimes called policy improvement. Okay, so I'm going to look at the current action value functions. Like the action value functions basically tell me I take one action now, so take some action A now, and follow pi t, follow the previous policy. What is the simplest thing I can modify the current policy to do better? Given what I know I will get for following the status quo. Right? And this is just like the greedy update. So right now I'm going to define, at this point I'm going to define a new policy. That takes the best action, assuming I will just get some reward using the current policy. So yeah, so there are a lot of notations here. Here's a picture that describes this idea. Right, so I'm maintaining some policy and try to improve it over time. So what I'm going to do is alternate between two processes. Q. They're the same. Right, so I will take the current policy, let's say pi t minus 1. I want to understand how well this is. This is the evaluation. Right, so this is something I can do in principle because within the planning setting, the environment is presented to us. Okay, so given the current pi, I can evaluate the values, either the state value or the action values. Okay. Once I get these value functions, I can do something about it, right? So, the Bellman equations or the Bellman optimality equations is hinting at some idea that, well, like if I follow the same plan as before for the next steps, what can I do currently to improve my reward? Okay, so that's basically assuming I will follow the same plan in the next step and so on. What can I do today to make it better? Okay, so that is the greedy step. Okay, so this estimated or learned value functions will inform some sort of greedy step. Okay, so okay. So it takes a second to show that this greedy step actually don't screw things up, right? So you actually have some improvement. So I think we have time to state the result. But policy iteration is kind of a fascinating idea, right? So what is, like, there are lots of notations in reinforcement learning or planning or MDP. A lot of the algorithms is really about playing around these two objects, policy and values, okay? Right, so if I give you a policy, you can evaluate how good it is. You can generate a bunch of value functions. And once you have a bunch of value functions, whether it's state value or action value, I can start thinking about like tiny bit of local improvement at every state or every step. Right? So this is like, the greedy step is sort of like thinking about like, what can I do differently? Like the current time step, I choose a different action A that might be different from the previous policy, and assuming I will still follow the same policy. But this assumption is actually not true. Like, because you're making modification almost everywhere, you actually generate a rather different policy. So it takes a minute to show this as improvement, but there's like sort of a competing force here, right? Like, you take the current policy, right? You generate or learn these values to evaluate how good the policy is. Once you know, this is a competing, force, because once you tell me the values, I will have this urge to improve it. Like once you tell me the values, like, wait, I can actually do a little bit better on this state based on the values. And therefore, I will have the incentive to act greedy. But once I become greedy with these estimates or with these value functions, these values become invalid again. So you have to like go on top and like do the evaluation again. So policy iteration is really this idea, and we'll revisit again next week. So let me show you one last thing. It may not be clear to you why this is an improvement. Right? This greedy is like making the modification based on local improvement. Like at current state, how do I do better? But it's only improving for this value. So it's not clear it will improve the overall objective value. Okay. So the question is the following. So we would like to show some sort of monotonic improvement. So it seems like we have done something that at least feels like a form of local improvement. Right? So by the fact of the greedy rule, I know that for any state and time step, if I look at the updated policy, let's call it pi t. Okay, so this is exactly what's being done in terms of greedy, right? So like, if I'm looking at the next policy, which is like pi t plus 1, this is kind of the greedy. I'm just being greedy for now, and for the rest of the time, I'm going to follow the current policy. So this is what this is capturing. Take the greedy step now, and then just follow the rest of it. The rest of the plan according to pi t. This by definition is the maximum of these action value function. And of course, this is only going to be bigger than whatever you get if you follow the same policy from now on. okay? This is sort of a local improvement statement because it makes the assumption that I will follow the status quo policy from next step on. And I'm only making one adjustment. But that's not exactly the policy I get out, right? So I'm going to make modification everywhere. The thought exercise is enforce the local improvement. The question is whether it will get you, whether this will actually imply global improvement. Okay. So, yeah, maybe not surprisingly, the answer is yes, and is sort of given by a very beautiful result, mathematical result called the performance difference lemma. Okay. So this is called performance I believe is due to Pagaday and Lamford more than 23 years ago. Okay, so the goal is to show that these local improvements, like assuming we only make one time step change and follow the plan, the resulting policy actually get you something better. Okay, so I'm going to write it. So the performance difference lemma is basically just showing that if you look at the difference in the overall objective value, okay, so this is like pi t plus 1 is what you get out of the greedy update. But I'm now not just looking at these like action value functions. I'm actually looking at the overall objective. That's the thing you really should care about. This can be written as some quantity okay, so I'm going to use this tau to denote trajectory generated by pi t plus 1. Okay, so I might erase the notation, but like you can think about this tau as a trajectory that's hiding a long string of the sequence of state actions rewards that's experiencing by using this policy pi, pi t plus 1, sorry. This difference in overall objective will be decomposed into a bunch of local improvement. Okay, so I think I'm going to copy these two things. Okay, that's one. Okay, that's it. So apologies for the notations, but you know, these two terms look a little dense, but I'm literally just copying the two sides of the inequality down here. Okay. So how do you read this theorem? Okay, so what's the left-hand side? This is what we want. which is the global improvement. Okay, so like how much better would I do by doing this greedy update? Okay. Well, I don't know, like, I'm making this policy update in a slightly funny way. I'm like doing this greedy update here and there, assuming like the future is taken care of by pi t, okay? So I'm updating to be pi t plus 1. But during the update, I have this funny thought experiment that I pretend the future will be taken care of by pi t. It turns out that this thought experiment is sufficient to ensure that you always get better, right? So even though the resulting policy is using this pi t plus 1 to take care of the future, this improvement from local update is carried over to global, because what this statement is showing is, the global improvement is just related to the sum of a bunch of local improvement. Okay. How big is this thing? How big is this like local improvement? Just shout out some words you know. How bad can this be? Like, this thing is like bigger than 0. It's like an underwhelming answer. But the point is, the way I'm updating pi t plus 1 is being greedy. By being greedy, I'm just like ensuring this term is never like negative. Greedy is always better, because I'm just making making a greedy choice based on this q of pi t. Okay. It turns out the total improvement you get globally, it's just sum of all these things. Right? So sum over all these like local improvement. Okay. So hence, like this greedy choice that you might have some suspicion with, like it feels like something is not exactly matching the global improvement. Turns out there's like a clean way, this performance difference lemma, to tie it back to ensure that this local greedy update, the local improvement, ensure the overall policy is always better. Okay, and this quantity I won't have time to define is sometimes called the advantage function. Yeah. So advantage function in English means I'm going to take some action now and follow some policy. Another comparison I could have is I'm going to follow the policy from now on. So advantage is really capturing, if I make a single unilateral deviation at the current step, how much better can I get? This is really focusing on this greedy local improvement, and advantage is capturing how much local improvement you can have. So this quantity is, in the lecture, is going to be used as an advantage function. Okay, so I think, so MDP is a very deep topic, lots of mathematics, lots of variations. You can spend multiple semesters on this. Today I'm mostly just trying to set up the ingredients that will be useful for the next few weeks or the next 2 months. And we'll switch between several topics of reinforcement learning, imitation learning, and inverse RL. Next Tuesday, we'll have an interesting lecture by Drew on imitation learning. And we'll get at a slightly different perspective of how to solve this sequential decision-making problems. Right? So today, we're mostly thinking about how to solve planning problem, where the reward or transition is known, like the transition and the reward function is known. like someone tell you what it is. We'll start to relax these sort of assumptions, and gradually you might start thinking about what if the state space is large, the action space is continuous, what do you do now? Like, the next lecture for the perspective of imitation learning will make the first relaxation or the first, complication. What if like nobody even tell you the reward function? It's actually kind of hard to define what reward means if you give me a task. Like what exactly is a reward function for driving a car? If you think harder, like there could be tons of details you can incorporate. But instead, only someone demonstrate how to solve a problem without telling you what the reward is. So that will be the topic of imitation learning, and please come to lecture on Tuesday.